Okay. Yeah, welcome everyone. Today, I'm not sure if you need, we forgot to go through problem 2 on exercise set 2 yesterday. So I don't know if would like to have a short discussion on that problem, or is more or less clear for all of you. Yeah. It was about calculating the number of wells that you need to deliver this 80,000 standard cubic meter per day of gas for 5 years. Okay, so let's take that before we go to offshore structures. That should have been, reviewed, but I forgot yesterday. So problem 2, exercise set 2. Okay, and basically you have a reservoir that you want to produce. You have a customer. You're going to work in a contract basis. They required a Q plateau of 80,000, and they also want a T plateau at least of 5 years. And the way we can visualize that field, it's we have a gas pocket. Okay, we have a reservoir, and then we have basically standalone wells, and that's how many fields in the US are built. And each one of them has its own separator. Okay, maybe they are close, they are a bit far away, but each one of them has its own separator. Okay. So you have to define, knowing how a single well behaves, you have to define how many wells do I need to ensure at least that I'm producing that much for that amount of time. So that case, if you remember, we apply equilibrium. Okay, we can apply any place we want. Okay, but it's typically at the wellhead. So we say P wellhead, and we get two curves that's flow equilibrium for single well. Okay, and we come co-current from the formation PR, which will be common for all of them. All of them are draining from the same tank. Then we go all the way to the wellhead. Let's put the choke someplace here. And we obtain a curve that looks like that. And then from the separator, if we say that line is very, very short, we can simply say, well, that will be that. Okay, P separator. And that's for P wellhead available. Okay. And we know to operate in plateau mode. Let's say I want to produce that rate, this Q star that I have here. I know I need to choke. Okay, I know I need to perform choking. With time, as I start to drain that tank, as I start to drain that reservoir, this curve doesn't change. Okay, that curve I always keep at the same separator pressure. The curve that changes is this one, and actually becomes smaller and smaller. Okay, that's for PR1, PR2, PR3, and here PR3 is smaller than PR2, and is smaller than PR1. Okay. So what I have done on this, you have received an equation that was the potential equation, right, for a single well potential. Has a function, I think it was a linear equation, right? Okay, that equation, which was, we can call it Q, production potential of a well, minus M times GP, cumulative gas production. Okay, and that equation comes from the fact simply that reservoir pressure with material balance, reservoir pressure can be expressed as a function of GP, okay, of cumulative production. That's the material balance equation. And then with equilibrium, I can calculate this point. Okay, I can find the Q well maximum. Okay, as a function of PR. And if I have this value, okay, for every PR, then I know if the rate that I have or that I want, I know if it's below this rate, the equilibrium rate, it will be feasible. Okay? If not, I have to adjust and produce exactly, let's say reservoir pressure drops here. Okay? It's below the Q. Here Q equilibrium is less than Q star, so then I have to change, I have to reduce the rate, because I cannot produce any longer that rate unless I add energy to the system. Okay, so instead of doing all the steps you have done in previous exercise, going to material balance, finding PR, and then finding this equilibrium point from equilibrium, I simply compound everything in that equation. Okay, and that equation we have discussed before is the single well production potential. Okay, and we know for the field, okay, the production potential of the field will be simply the number of wells, because all of them are standalone. Okay, so simply will be the number of wells times the Q potential of a well minus M times GP. Okay, still the production of each well will depend on GP. Okay, and that depends how many wells I'm using. If I'm using more, the GP will change. Okay, but the production will be multiplied, and simply we're saying this is assuming that there is no interference between wells. Okay, it might happen if you drill the wells too close, they start stealing production, so the production is reduced from one of the wells. We are neglecting all of that. We are saying simply additive. Okay? So one way you solve that problem, many of you made like what we have done before. You did it with time. You divided your horizon in a few years. Okay? Then you calculate your GP, initially will be 0. Then you calculate your Q of the well potential. And then you calculated the Q of the field potential. That this will be simply number of wells times the Q potential of the well. Okay, and you started simply with a number of wells that you assumed. Okay, initially I assumed I have 1. And then I had a column here, exactly what you have done or what we have done on the simplified reservoir simulator, that is actually the Q of the field. And the Q of the field had a logic inside. Okay, so this cell will say if the Q of the field that I want is, if the field potential, okay, is greater than 80,000, then just put 80,000. Else, that means it's below, okay, then the Q of the field will be simply equal to the potential. Okay, so you will always be declining after that point. After you pass that point, you will be always producing that rate. If you don't change your system, you don't add energy, you don't maintain pressure, you always have to follow that line, okay, the potential line. And that's fine. Another approach, so that's approach, let's call it here approach number 1. Okay, and you simply went and you say, well, if I use one well, with one well you cannot produce. Okay, it's not enough to produce the 80,000 from one well. So you need at least two. So you were changing 1, 2 until you reach to this number, which is 3. Trial and error. Okay. Another approach some of you used is on this production potential curve. If you remember, the potential Q of the field potential versus GP is a straight line. Okay, so it has that behavior. So you have if I have more or less wells, okay, it will be just scaled down. Okay, if I have, for example, n wells equal 3, n wells equal 2, n wells equal 1. Okay, but so if you want a plateau rate of 80,000, right, and you want a time plateau, a duration of the plateau for 5 years, okay, with these two numbers you can compute the GP that you should have at the end of the plateau. So the GP at plateau end, okay, will be simply 80,000 times 5 times the number of days per year. Okay. Okay. And you know exactly at that point, exactly at that GP, okay, your potential should be at least equal, or it should be higher than 80,000. Okay. If you want to produce at least for 80,000 for at least for 5 years, your potential, so the Q of the field potential at GP, this GP, okay, with a long name, plateau end, should be at least bigger or equal than 80,000. Okay, so I have taken time out of the picture by doing that. Okay, I know that equation relates only rate and cumulative production. In reality, I know it's a process that goes with time, but by using simply that, by converting these values in cumulative production, I took away the time from the equation. Okay, and then I say, well, I have an equation for that Q of the field potential, so I can take that equation, Q of the field potential, and that will be this Q PPW minus MGP times number of wells. Okay, and I can apply it exactly at the plateau end, exactly when I have that when I have that end of the plateau. So I say all of these are constants. Okay, QPPO, MGP, let's call this GP star. Okay, it will be easier to use. And I know that number exactly when I evaluate at that GP should be bigger or equal than 80,000. Okay, then I have everything. I have this and these two constants. I simply clear out and tells me the number of wells should be greater or equal than 80 divided by Q PPO. Okay, and that's how you find that's another way to find the number of wells. Okay, but that's assuming you drill those wells from the beginning. Okay, you have the system, the potential of your system is like that from the beginning. Okay. Okay, so it's likely two ways to solve the same problem, but the two of them are very valid. This one, the first one, is a bit more intuitive. Okay, we do it the same way that we have done all of our calculations time by time, and we check the equilibrium. The toughest part was to understand that this equation was giving me this point. Okay, that was the toughest part. The other part, a bit more abstract, that simply you have to think about in terms, convert everything to GP. Okay, and then use the equation. But basically they give you the same result. Yeah. Also there were some for the post-plateau production. Okay, there were some of you that used method 1. But I saw one group that used also a smart method, which was, you remember the derivation we had in class, okay? That if the production potential curve QPP is linear, okay, then you had simply that for times less than the T plateau, simply the Q of the field will be Q plateau. But if the time is greater or equal than T plateau, smaller or equal, then you have to use Q field will be equal to Q plateau times e to the minus m t minus tp plateau. I think so. Okay, let's check the previous classes. Okay, we're assuming it's linear. It's a linear relationship. That's exactly what we have now in our case. And we come to that equation where we have the integral of the variable and the variable itself. Okay, we have here an integral of the rate, and we know the rate will always be declining on potential. Okay, so we come with this expression. Okay, and then the matter is to find T plateau, that it will be Q PP of the field divided by Q plateau minus 1 over m, I think. Okay, so even though that derivation, we know that it's linear, for example, for an undersaturated oil case, just neglecting tubing, everything, just IPR. In our case, we were provided, and for gas, surprisingly, it is also a very fairly straight line. Okay, which very strange, but surprisingly is like a straight line. Okay, so what we have done, we don't know exactly what this QPPO has inside, this M and this QPPO, but we know if the production potential is linear, if we integrate it, it gives me an exponential function. Okay, and then if I change the number of wells, that's going to affect this PPO and it's going to affect this M. Okay, simply by multiplying. The M for the field is the M for a well times number of wells, and also the QPPO of the field is the QPPO of a well times number of wells. Okay, so that was another way I thought was smart, just assuming the same because it's linear, so you can say that the integral will give you an exponential function. Okay. Yes, so I think that's all the discussion we had to make on exercise on problem 2. Is there any question before we move to the next to the next topic? No? Okay. So now let's go to this part, which I think is very important. Is for offshore fields, is extremely important to take into account the marine part. Okay, so basically the topic now is offshore structures for oil and gas production. Okay. So is in a way, we are going to see now it can have the wells inside, so it can have my production system, okay, but it has also many other things. It has the processing, is what is in charge of taking that oil and gas and water and process it and make it ready for the market, making ready for reinjection, making ready for transport, for many things, okay, and you have a lot of things inside. So I think instead of I listing, because that will be a bit boring, so let me just copy it from here, all the things that are typically included in what I call the offshore structure. Okay, is that big enough for you to read? Yeah. Okay, so one thing we have, okay, and we have to make here a comment, okay, these are not, all of these are in the same offshore structure. Okay, sometimes you have simply one that has everything, okay, but sometimes you want to split, to have part of it in one, part of it in another. Like you remember in this field Peregrino that you had the exercise on, okay, we had the wells in some platforms, and we have actually two platforms on the side. Okay, and from there you had a very small separator, you had a pump, you had some facilities, but then it was sent to a Fpso where you had all the main separation. Okay, everything else was on the Fpso. That's the Peregrino field. Okay, so in that case you had the drilling package, you had some facilities in these two platforms, but all the rest that has to do with the processing is actually on the Fpso. Okay, so one thing we have, and I put here, is not really maybe the most important, okay, it's the drilling, what we call the drilling package. And this, what by drilling package I mean the drilling tower, and I think we have a picture. You can identify it very easily from photos. Okay, you see this big structure, very high, okay, coming out of the, sticking out. That's actually what we need to hoist the pipes up, to put pipes inside the well. Okay, drilling tower, blowout preventer, drilling floor, mud package. Okay, that's also, I guess you're also familiar with the mud package. Okay, but basically I have the drilling bit, so I have to have a system that ensures circulation. This mud, I take it up, then I have a big system where I have the shakers to remove the cuttings out of this mud. We have filters, we have all kind of things. Then we have a pit where I mix, I keep the suspension in solution. I also add new mud if I have to replace for some reason I have been losing mud. And then finally I have a pump, okay, that takes it back all the way to my, and that takes space. Okay, that if I need to have that, and I really, that's one of the things we have to go a bit in detail. If I really need to have that, that takes a lot of cost and a lot of space in the offshore structure. Okay, the cementing part, also I need pumps for doing cementing. Then, and also shouldn't be overlooked, I need to have storage deck for drill pipes, tubulars, and drilling risers. Okay, because I'm inserting pieces of pipe, screwing them down just to make the drilling, to make my completion. So I also need space, okay, and it looks something like that. Okay, a lot of pipes, very long joints. How long are each joint? No drillers here?
30.
No?
30.
Well, you have to ask your friends. 30 feet or 30 meters?
It goes feet.
Okay, but basically a collection of long pipes that you have to store, and that also takes weight, so you have to make the structure to bear that weight. So if you really need, all this discussion is just to say this one is optional. You don't have it in all. Okay, you don't have it in all offshore structures, and if you have it, you really need to justify, or has to be really clear why you need it. It's a big investment, okay? So you really have to be sure that you need that package, okay? And that's really heavy well intervention. If you have to change the tubing, you have to change your completion, you have to re-perforate, you have to create a sidetrack, you have really to, it's very expensive. Okay? While we go to light intervention, are things that I don't need to have such high, carrying capability. And I don't need to circulate mud, for example. So in that case, we are talking about wireline operations. Okay, we need to change, we need to make some cleaning in the well, we need to try to shift a sleeve, for example. We have coil tubing. Okay, we want to maybe take out some scale, and that's something more common. That's something that is present in many offshore structures. Okay, and then we have what is actually the heart of the structure. Okay, and really a very important part, takes a lot of space, which is the facilities to process this oil, gas, and water. Okay, and basically what we have inside, also might be repetition, but I think for clarity it's important that we mention it. Okay, typically oil and gas processing facilities for oil and gas. Okay, so we have first oil, gas, and water separation. Okay, and that is typically done in big tanks. Okay, this is done in big cylindrical tanks, so that takes space. Go. Okay, like let me show you. I think I have a figure. Some components have a lot of cylindrical tanks that have a lot of components inside. It's a lot of steel, and if you want to increase that rate, that's part of the discussion we had yesterday, then you have to increase simply the volume of that tank. When you have to make it bigger, or you have to put more tanks in parallel, then that cost becomes simply by weight of steel, manufacturing cost increasing, but also the structure has to support those vessels. Okay, so after that, what do you have after this step? You come out with gas, you come out with oil, and you come out with water. Okay, with the water we need to have a water treatment. How do we call it? Produced water treatment. And then I come here that if I also I need to make for disposal, that's simply dumped to the ocean, or I need to have reinjection. If it's reinjection, I have to increase pressure. Reinjection. I have to use a pump basically to send that down. Okay. For the oil, what do we have? For the oil, typically we have simply dehydration. Okay, we have stabilizing. We have some heating of this oil, and also we might have some desalting. It's not so typical in the North Sea. Okay, and finally we come to tanker is the most common in the North Sea, or you can also use pipeline, export pipeline. Okay, so you need to have a facility to offload that oil to the tanker. Okay, to transfer the oil from the platform to the tanker. What else do we have on the platform?
Flaring.
Okay, flaring. That's right, but let's go first for the gas. Okay, for the gas, also one thing that we have that takes some space is the dehydration. Okay, we don't want water or any liquid downstream, because then that gas we can take it to compression. Remember, compression doesn't like liquid usually. Okay, there is only one compressor that likes liquid, and that's on Gulfax. All the rest don't like liquid. They're a bit particular. Okay, they just don't accept any liquid. So for compression, you have to dehydrate, and then you can send to different places. You can send for pipeline export. Okay, you can re-inject to pressure support. You can also and you can also use for lifting. Okay, for gas lift, for artificial lift. Okay, you also take a bit for power generation. Okay, so typically up to that part, that's the minimum, I think, in terms of processing that you have on the platform. There are other things for gas conditioning, removal of mercury, but usually in the North Sea we don't come that far. Okay, you have another step, which is gas conditioning. Okay, dew point control. You can find that in some facilities all around the world. When you come with, for example, H2S removal, you have mercury removal, but typically in the North Sea we don't have that part. Okay, we don't have, not so common for the North, not so common. Okay, then let's see what else we had on the list. Gas injection system, gas compression units for pipeline transport. They don't take that much space, but they take power. These are the most power that have the highest power consumption. Water injection system, also pumps, they need to run. Living quarters, heli deck also, we have it here. Okay, we need a power generation unit. Typically, some facilities now they use power from shore or power from another installation. Okay, but typically we have to have, that's done by gas turbine. The flare system, when I have a stop of the system, I have an undesired event, I have some so then I have to use a flare to burn that excess hydrocarbon. Okay, just to make it safe for the people on the. Then you have utilities. That's something we don't think too much and we typically neglect, but are important. The hydraulic power fluid. Why do you need this for?
Control.
To basically the main is to open and close valves. Okay, to open and close. And they are very important. Okay, you have in the wells, you have in manifolds, you have valves everywhere. Compressed air, drinking water, some things that have to do with the people, air conditioned, ventilation. Okay, and this one, the bay for wellheads and Christmas trees, is also optional. Okay, it's also very optional, and it's related actually with that drilling package. Okay, that's only if you have dry Christmas trees. And we're going to discuss a bit more on that just in a few. Dry Christmas tree. Okay. Production manifolds, we're also going to discuss that. We have an arrangement of pipes that they do something. You use it for typically for testing. But I'm going to save that discussion for now. Also, something that is typically overlooked is the storage. You might have storage on your facility. Facilities for oil offloading, that's to tanker. Okay. Control system, monitoring system, and also something we're going to cover a bit later in the course is storage, injection, and recovery of production chemicals. And this is to avoid issues like, for example, wax deposition, scale, hydrate, corrosion, etc. So these are like the main and the ones that are the most relevant and the ones that take also the most space. Okay, so let's just present what kind of structures, what type of structure we typically have, okay? Type of offshore structures. Remember, it's a big part. First, it has a crucial part on many things, okay? It houses the wells, houses the processing system, but also is a big part of CAPEX. It's a big chunk of the CAPEX. So that's why the selection, which one we should use and how do we select it, is something we have to take into account, okay? You might gain by changing plateau duration, by changing plateau rate a few percent, but if you select incorrectly something that costs billions of dollars, that might have more impact, okay? So it might be a very good nerdy work on the reservoir engineering part, and then you come and you select, no, use whatever you have there, okay? It doesn't work like that. It's a combined effort by many different teams. Okay, so we have two categories of this offshore structure, and first I want to start by saying they can be bottom supported. Okay, going to have a category here, or they can also be floating. And inside here we have two categories for the bottom supported. We have fixed and compliant. Okay, we have two categories here. And on the floating part, we have also two categories. We have one that are neutrally buoyant, or we have one that is positively buoyant. Okay, so what do you think we have? Let's start first with the easiest. On the fixed bottom supported, what do we have there? A structure that simply is like, it's not going to move significantly. You're going to put it in a place and it's going to stay there, and it's going to be supported by the ground, okay, by the sea, by the seabed. What is the first one that comes to mind?
Fixed platform.
Just simply a jacket, right? A steel jacket. What else do you have in this part?
Gravity-based.
What Norwegians like very much, okay, they have been using for a long time, concrete structure called GBS, gravity-based structure. We're going to see some pictures just now. Okay, and what else do we have in that category? It's also like a jacket, right? But it can be removed after, so it can just, it's like a mix between a jacket and a boat. A jack-up, okay? Jack-up. It's not so often used for production, okay? It's more used for drilling. It's a structure actually, yeah, I'm going to show you some pictures now. Okay? And compliant, you have a very special type of a structure. We don't find it in the Norwegian continental shelf. It's for very deep water, but it's called basically compliant tower. Okay? Found very much in the Gulf of Mexico. Okay? Fixed, basically, it's rigid. Okay? It's very rigid. Compliant, it allows some movement. It's still rigid, it's supported from the base, but it allows some movement. Okay? Now, neutrally buoyant, what do we have? Floating structure, which is neutrally buoyant.
Semi-submersible.
Yeah, but what is the preferred guy? Like for every place in the world, the most popular, simply a boat, right? A ship, a Fpso. Then we have semi-submersible. Okay, what else do we have?
TLP.
We have also TLP. Be careful. TLP is also floating, right? But that it comes in this category. TLP stands for
Tension leg platform.
tension leg platform. But that's a very special design, okay? It's not actually floating by itself freely, but it is something holding it to the ground. It has something holding it to the ground. So that's why we call it positively buoyant. If you let loose, cut this support, it's going to float. It's going to be at another position. Okay, so that has some positive buoyancy. Okay, neutrally buoyant is that it simply stays floating on that place. Okay, and one more thing we have here is another type of Fpso called Sevan, that you might have seen it before. Fpso. I think it's also a Norwegian company, I think. Okay.
7.
Yeah, Sevan. Sevan. I don't know how that you spell it in English. I think in Norwegian it's Sevan. Okay, so now let's see. So our intention is, that's like the whole overview. For drilling, be careful. For intervention, for deployment of subsea systems, deployment for drilling, we use another type of vessels. We are not going to cover here in this course. Okay, we are kind of neglecting passing. We know there are other courses that they cover very well, you know, subsea intervention, drilling, so that we leave to them. We are looking just at the structure, which is for production, for oil and gas production. So I think I have, let's see, before we take a break, we see some pictures. That's an Fpso. Let me maybe take that. That is on the compendium. Okay. Okay. The main difference on the jacket. How do you hold it? How do you hold the jacket in place?
Put the piles.
Okay. So you have something that is called a pile. Okay, on each part. And you simply hammer it, okay? You hammer it down until it goes deep inside, such that it holds, it connects the steel structure, which is a bit light, okay? If it comes a very strong forces, marine forces on the structure, and it's not fixed, it might move, okay? So these piles are the ones that transfer, and they tight the structure to the formation. Okay, then you have this gravity-based structure. I think I have another figure, a bit nicer here. Okay, that's a jacket being transported. You know, you have to fix it afterwards. Okay, huge. I don't know where that is taken from. That's the gravity-based structure, the favorite of the Norwegian for a long time. Okay, they had a very strong concrete industry, so they came with that, and it's also heavy. You have concrete, it's also heavy, but how do you fix that structure in place? It's helping simply gravity, right? But the other mode it has is, you might have heard about it in the subsea course. Templates, many things are fixed by suction anchor. Okay, so like this, you have a cavity, you have the sea floor. Okay, you come with a cavity that is filled initially with liquid. Okay, and you connect a pump to that cavity, and you start extracting the liquid out. You create a vacuum basically, and that vacuum simply brings down the structure. It makes it pile to be inserted even more when you start pumping. After pumping, Okay, and this mechanism, we use it for many things, especially for subsea systems. Okay, you have drained the water, okay, and the soil, okay, the soil simply something like that, okay, and that gives actually some stability to the structure besides its own weight. Okay, that's called suction anchor. Let's take a break, okay, let's say 15 minutes, and we come back to our discussion. Okay, one thing to note is that jacket typically doesn't have any storage, and also typically wells are drilled. Sometimes the jacket has a drilling package, okay, so wells are drilled from the jacket. Also, it's not something that we can easily reuse, so typically it's just built for the field, lasts for the life of the field, and then is simply scrapped and recovered. Okay, gravity-based structure, a similar story, is typically just built. Here is more difficult to scrap it, so typically they cut it some meters close to the surface, and they leave there like some notice for future traffic on the area to be aware of that. One thing with gravity-based structure is that they have storage, okay? And we're going to see now that's a very important consideration for selection of the structure. If it's going to be in an area that you have backup, you have easy access, you have no tough weather conditions, then you don't need any storage. But if you're going to have all of that, maybe some blockage due to ice, then you need to have storage in case something happens. Very rough weather, very strong winds, but let's keep that for later. Basically, the idea is that jacket doesn't have storage, GBS has storage. Okay, GBS is held by its own weight, very difficult to remove completely. Jacket sometimes you can remove completely. Okay, and in both of them, wells are usually drilled through these legs. Okay, you can have also wells subsea coming to the structure, but you have many wells coming through these legs. Okay. Then we had the next one in our list was jackup. I don't think I have a very nice picture of a jackup, but it's similar to a jacket. Maybe I have this one here. Okay, but it's basically a floating structure. It's moved from place to place, being towed or being floating, and then when it's going to be on that place located, then the legs are dropped, are just lowered. Okay, so if we see maybe a very bad sketch, but if we see it on the transport mode, it will be something like that with the legs retracted, and typically has 3 to 4 legs. Very professional sketch. So okay, and when it starts exactly on place, just lowers the legs, and then by lowering the legs is starting to pull up and separate from the water sheet. Okay, and the intention in a way of a jackup is that you can reuse it. So that's why it's pretty much used not so much for production, but mainly for drilling. Okay, when you want to drill in shallow waters. But sometimes you have, I think there is a field, actually the Volve field, I think it was a jackup. Was a group here working with Volve? No. Okay, but I think they were using a jackup. Okay. Then we have this compliant tower that basically, if you try to make like a jacket structure self-sustained, you know, if the water depth is too big, and here we're talking 500, maybe 600 meters, okay, it will be extremely wide. Okay, it will require a lot of material, will be heavy, will be difficult to manufacture, transport, and expensive. So they basically allow it, they make it with a more uniform cross section, okay, but then sometimes they are held in place, or it helps to be held in place with some lines, okay, with some tensioners, such that it's allowed a little bit of movement on this direction, but the tensioners keep that movement restricted, okay. Then you save some cost, some material, but you can make the structure much taller. That's very typical for the Gulf of Mexico, okay. We don't have them here in the North Sea. And then we have Fpso, okay, and these ones also don't have any storage. Jacob doesn't have any storage, okay. Fpso, there is something actually, let me take a picture of an Fpso, and there is something special and interesting to look there. Sorry for all the images, but you have to find a way to make your notes such that they're not spoiled by me pasting images all the time. So okay, this we have used already. Okay, so Fpso, a ship that has a lot of stuff on top, doesn't typically have a drilling package. In the GBS, in the Jacob, they usually can have a drilling package. Here it doesn't have. Here you see the flare that we were discussing before. Okay, but here there is something particularly interesting, which is you have to bring the pipes. The wells are not that's floating, okay? It's have a significant movement on this direction, on any direction, we will see. So wells cannot be placed there, the wellhead, okay? So wells are typically subsea, and you have your Fpso, and the production is carried to that Fpso using a riser, okay? Using either a main pipe or you use many risers for each well. We're going to see a bit what defines how many risers you have, but that's typically a riser, okay? That you take production, you commingle production from different wells, and you take it up to the boat. But there is one special thing. If you see it from the top, okay, from the top, the boat has like this shape, okay? Okay, and the environmental conditions, the marine waves, the current, also the wind, is not always in the same direction. Okay, it's changing direction. Okay, so for example, if they are like that, it might be okay. Okay, it's exactly oriented on the direction where the waves or the wind is coming, but they might be also coming from the side. Okay, so in that case, if they are very tough or very aggressive weather conditions, it cannot just stay in the same position, in the same place. The Fpso has to rotate to adjust to those. So for rough weather conditions, okay, and varying also on direction, on magnitude, the Fpso often have to rotate. Okay. So you see that creates a problem. You have the pipe coming just up the boat, and then you're going to twist it. Okay. What happens if the pipe don't like to be twisted? Okay, all the time. They're going to break eventually. So the way we fix that problem is on the Fpso. We create a structure called a swivel. Okay. It simply might be a round structure that is going to be fixed all the time. Actually, in this swivel is where we make the anchoring. The Fpso usually has to have, and all floating structures, they usually have to have some sort of anchoring. And if you see here, they're not anchoring uniformly in any place, but they are localized in one place, which is this swivel. Okay, that keep it somehow in place. They avoid drift, they avoid excessive movement. Okay, and they are fixed to that round structure, which is always fixed. And then you have a mechanism that allows the rest of the ship to rotate with respect to that swivel. Okay, so you're allowed, this one is fixed and this one is movable. Okay, not all FPSOs need that, depending on weather conditions, the change in direction, but you often have that case. Also, you have some FPSOs that have it on the, don't have it on the body, but actually they look from the side a bit like this. Okay, and here you have this swivel. Okay, and that's the entry point for the risers. Okay, let's use another color maybe. Okay, but be careful is the ability to move, to rotate. They have typically big storage. Okay, and here big, we are talking, in the case of gravity-based structure, I think the numbers are, they're on the compendium, but I think they're around 100,000 to 300,000 barrels storage capacity. But here we're talking more in the range of millions. Okay, from one, I think the biggest in the world has something around 3 million. Okay, so you can imagine if your field is producing 100,000, for how many, for how many days you can live without no tanker coming. Okay, so that's something, if you're going to be interrupted, your production, there is a risk that your tanker might not come to your field. You need to have storage in place to be sure to not cut production. Yeah. What else we had? Now this Sevan is not exactly the second on the list, okay, but it's this type. Basically, what have they done here? It's like an FPSO, right? But they took away all the rest. They just kept the center, okay? They say, well, we don't want to be dealing with rotating. Let's just make the center bigger, and that's all, okay? So that was a clever idea of these guys, especially for moving creates a lot of problems. It's like a marine, it's like a boat, so you have to have, captain, you have to have the maneuvers for moving. So they say, we want to keep it always in the same place, so we just make this structure bigger. Okay. In the North Sea, we have this field also up north called Goliath. Okay, that is by Eni, and it's using that concept, and I think it's used some other place. Okay, also has storage, but takes out the complexity of moving the ship. Okay. Then you have a semi-submersible, which I don't know if I have a good picture of that. No, but basically typically has, like it's shown in the figure, it has two legs similar to that. So let's see how I can make it. So it has one leg here, then that's the platform, then has another leg here. You have seen it. Is not so common in the North Sea, but it's very common in the Gulf of Mexico. Okay, it has two legs where you have the floater, the ballast. Okay. Then you have this spar that we are going to have our first one now in Norway. I think it's already in place. Which field is it? Asta I don't know how to pronounce it. Osta-Hansteen. How do you pronounce it in norsk? Asta-Hansteen? No? You know, you look like you're not Norwegian, so let's see. So Osta-Hansten, maybe, I don't know, Hansteen. Okay, that's going to be, no? Is it Osta or Asta? Asta-Hansten.
If there's an A, there's Asta. If there's an O.
Okay. Yeah, I'm not sure what name. Okay, so let's take, I think I have a picture of that spar. And we're going to see now why sometimes they use spar, okay? Yeah, I don't have a picture of the spar, so let's just take this one. Okay, this is like a cylinder, okay, where you have on top of it you place all of your facilities, but it's basically a very long cylinder. And if you want to bring any riser, if you want to bring any well inside, you simply do it from the inside of this cylinder, okay? But basically the intention is that you make the lower part very, very low, very, very big, okay? So it's forgot the name. It's a low drag, well, you basically make that area that is below the surface very, very long, okay, and very, very big. That helps with the stability of the structure. That helps that it will have less movement on the vertical side, on the horizontal side. It will help to reduce the, it's called low draft. I forgot the name. Okay, but basically you make that section very long to help to reduce the movement of the structure, to reduce the movement, the structure. And we're going to see now in a way why we want to reduce the movement, okay? Yeah, and you see here the type of mooring that we have shown before. Here is like simply hanging, okay, simply is with chains and they have tension when the ship starts to be off position, okay, so they start creating some tension to bring it back. But in the case of spar, you have this mooring, which is taut mooring, taut lines, that they have some pre-tension, okay, so they are made in a different way. Other thing to see that is interesting about this spar is this lines that it has. You have seen it also in chimneys, and I guess you know what is it for.
Make the flow turbulent.
Okay, yeah, to basically when you have a circular structure and you have the current, in this case you have the current coming on that direction, you have vortex shedding on the fluid comes and goes, makes the round, okay, but then it cannot exactly, it's like it has to take a very sharp turn, okay, to be back exactly to come out on this side. So what happens typically is simply it detaches early, okay, and you have a lot of turbulence and you have a lot of wake. Okay. Now, a funny thing about that is not always on the same position. It might be that it sometimes is detaching here. It might be sometimes it's detaching there. So it creates like a transient detaching. Okay. The wake of the fluid, sometimes it might be here, sometimes it might be here. Okay. So it creates a periodic change of the wake. And remember, that wake you have pressure. You have a change of pressure. Here will be positive, right? You have positive on this side, and you will have negative on this side. And that defines what is the force on the structure, on the spar. Okay? When the distribution is changing, now it's becoming more positive or more negative. That's basically exciting the structure with some frequency. Okay? So you put these guys just to break that. And create always that it always detach, always at the same position. Okay. So we call it here vortex breaker. Okay. You're not supposed to become experts from just one or two classes on offshore structure. There are many things, many details, but I just want to show you some of the issues that you have for each structure. Okay. Each structure has a set of qualities, but has also a set of problems we have to take into account. Okay, and the last one we had on our case was tension leg platform. And in this case, what is interesting is that if it didn't have this, what we call tether, okay? So let's make a sketch. That's the last structure for today. And it looks similar to a semi-sub. It has two legs. Okay, and you have here the rest of the structure. Okay, maybe. Okay, but so it's fixed in place by this tether line. By this, okay, tethers. Okay, and it's actually dragged down. It's not only simply floating, but it's dragged down. So that means if these lines, by any chance, you cut them, it will just go up. Okay, like if you bring something filled with air, a container, down on a bathtub. Okay, and the intention, basically, why do we do it that way? Okay, is also trying to reduce the movement slightly. Okay, if we have this tether, okay, which is creating a force, dragging it down. Okay, anytime you have a wave or something that moves it to a side, okay, let's say now you move it out of the center line. Okay, what are you going to get? The tether is going to be like that. Okay, and you're going to have two forces. Okay, so these forces are going to tend to bring back the structure to its equilibrium point. Okay, every time you try, something is trying to pull it out of the equilibrium point, these lines are bringing it back. Okay, so that in consequence allows it to have less movement than, for example, a semi-sub where you don't have that arrangement. Okay, and we're going to see why movement is important in a while. Okay, but you got the overview, fixed, very simple, those that are supported, those that are floating. Remember, you need to control in this floating the ballast very actively. You have a tank filled with seawater that you have to change. Also, if is filled with oil, for example, the oil is changing the ballast, is changing the buoyancy. So you have to be careful to always having to control how much you have, how much load you have on the boat, how much ballast you have, and how much storage you have. Okay. Okay, so that's okay with the overview of all the structures, but now we go to the center of the discussion. So how do we select offshore structures? Okay, and we are going to talk about some technical reasons. Okay, mainly there are many other reasons. There are some companies that they prefer some particular type of structure. Someone bought, they found a very cheap Fpso some place there, so they want to use it in a new field. There are all other types of reason, but I'm speaking mainly from from the point of the technical part. Okay, and there are a few things that we have to consider. One of them is water depth. Okay, and very roughly said, if you are below 500 or 600 meters, you have you can use You don't have force lift, okay? But you can use a bottom supported structure. That's the limit, okay? Actually, the compliant tower, I think the deepest is has 610 meters, okay, water depth. But if you are above that, okay, if you are greater than 500 and 600 meters, you have to use a floating structure. Very simple. Okay, I think I have an overview of what you can find is here. It's also in the compendium, I think. Okay, so just to see the overview, what we have currently, this might have changed. I made this 2 years back, so you might have some, but you see jacket, gravity-based structure, they cover all the way to 413. That's the current record. Bullwinkle, that's in the Gulf of Mexico. Then compliant tower, they use it for some overlapping wrench with jacket. But the deepest is 610 Petronius. I think that's also in the Gulf of Mexico. Then you see semi-sub, these are floating. So basically they can cover the whole range, okay? But they are preferred for deeper, okay? So you have one which is shallow, 80 meters. Maybe this is not to scale, I think. Okay, and going all the way to 2,414 meters, quite deep. TLP doesn't go that deep, okay, but you can still use it for quite shallow. SPAR is also for deeper development, more than 600. Neptune, all the way to quite deep. Perdido, that's in Brazil. And then Fpso, basically you can use for the whole range. Okay. So that really doesn't narrow down. It's a very roughly to tell you what should you use, but that doesn't really narrow much. Okay, the offshore structure. So the other criteria we use is the location of the well tree. Okay, you have basically two. You have dry and you have wet. That means subsea. Then the third point we are going to discuss is the oil storage, the need for oil storage. And the last point is actually the marine loads. And those are the 4 points, you know, that we are going to cover here in class. Okay, there might be some other things, but these are related to petroleum, the most important. Okay, so let's talk about the second point, which is, it's already running out of time, but the location of the tree. Okay. So how do we define what kind of tree do we need? Any ideas? Well, one of them is the water depth. Okay. I think the current limit for dry Christmas tree is 500 meters water depth, 1500 meters water depth. I think at least that was until a few years back. Okay, the maximum is 1500 meters. Okay, then another thing that has to be taken into account is the reservoir spread. Okay, or the reservoir structure. if, let's say you're at shallow, relatively shallow, that you can use a platform, okay, and your well in your reservoir is pretty much concentrated on the same place, you can simply drill all of your wells. That's not up to scale. Let's see. Okay, so if it's pretty much concentrated, that you can reach with deviated wells, okay, they have to be deviated wells, but from the same location, then you can use dry Christmas trees. Okay, because you can reach and drain most of the reservoir from one particular location. You need to use one, or maybe you split. If there are two big accumulations, you use two. So that's in the case of concentrated reservoir. But sometimes you have that becomes unpractical. Let's say you have a different either a reservoir which is very thin but is very spread, okay, that you will need, you cannot reach to all of it from the same structure, or you have a reservoir which is a multi-structure that has a lot of different structures. Okay, so in that case, it might be better simply to drill wells, subsea wells, that are simply on top of the structure. Okay, and having an Fpso. Okay, and it's simply a bit about the location of a bit about the reservoir spread. Okay, another thing we have to take into account is well intervention needs. Okay, when do we need to perform intervention? What kind of cases do we have to be careful? When we expect, for example, tubing replacement. Okay, let's say we expect some sort of corrosion, or we have to something that makes us replace the tubing very often. We have to be, in that case, not only because subsea, right? Subsea, we have to come with a drilling vessel, and then we have to go well by well. And if I have to do that every 6 months or every 2 years, will be very expensive. Okay, if I can simply have all the wells from the same location, okay, and I have, for example, a platform with a drilling package, that will be much more economic. Okay, that might be tubing replacement. If you want to make something with completion modification, changing the completion. We discussed a bit about that when we talk about downhole networks. Okay, all the things you make to try to improve the flow, the interface with deformation. If you have, for example, artificial lift. Okay, and in particular, the case that we already discussed, Peregrino, using ESP pumps. Okay, the lifetime of the ESPs might change from a few months all the way to 2 years. But if you already know you have a subsea well, you have to make intervention on a field that has, how many wells Peregrino has?
40.
40 wells, okay. So you have to make 40 intervention coming with a vessel, subsea. It's going to be a lot of money, okay. So you prefer to have, that's why they went for a jacket where they had a drilling package. And they can go and replace the pump when needed, okay. So here, basically, the conclusion is that if frequent intervention is expected. Then I go for dry. If frequent intervention is not expected, then I go for wet. Of course, if the depth allows. Is not expected, I go for wet. Also, one thing I have to, and of course here I should have with drilling package, okay? Okay. The other thing I have to take into account if I expect a lot of infill drilling. Okay? If let's say I have plans that in the future I want to create a sidetrack from one of the existing wells, okay? Or I want to drill more wells at a later stage simply to prolong the plateau or to produce more or to drain from a region that is not being drained properly, then I also might want to go for dry if drilling, yeah, if yes, then you go for dry Christmas tree, and preferably with drilling package. Okay. Of course, there is we have to, if let's say in the case of the dry Christmas trees, okay, you have to leave. Let's say it's a jacket. Okay, so if you're planning to drill many more wells, okay, you have to have the space and you have to have the support and you have to have enough to be able to support those wells. So if you're expecting, let's say, to double your amount of wells, you initially will have to build a very big platform that half of it will be empty. I'm just paying for the space that I'm not using yet. Okay, so that's something also something to consider. Yeah, so what was water depth? Okay, and here I wanted to take, it's 53. So I just show you how it looks like on, okay, that's what we call the well bay. And you see it's quite crowded. So if I have plans to drill, 20 more wells here, they're going to scream, okay? Because they say we don't want to make that bigger. Then we have to make the platform bigger, have to make it more expensive, only if you need, okay? Only if you need. Yeah, I forgot something here. Okay, so going back to the offshore structures, the only offshore structures that allow dry Christmas tree are which ones? Basically jacket, right? We have the jackup, we have gravity based structure, basically all of them that are bottom supported, compliant tower. Now any of the floating structure allows for a dry Christmas tree. Okay, it's going to move, right? This structure, we know it's going to be floating. Like for example, Fpso is going to be floating, right? It has too much movement to have, let's say you have your well, okay, you have the seabed, you have your well that has been drilled through the reservoir until the reservoir, and then it's going to go up and it's going to be on the boat here. Let's make here a hole. Okay, and someplace here you have to put, you have to put a hose and you have to put here a connection to the facilities. Okay, so that pipe cannot be moving, being squeezed, okay, being changed up and down, because it's going to crack. And if this pipe cracks, then you have a spill, okay, you have a undesired event. So that pipe usually should be kept in the same place, and then you have the boat moving around that pipe, okay, around that well. Okay, and for that we're going to see maybe next class, we have to put some motion compensator, okay, such that we keep this one in the same place but the other one is moving. Okay, so for Fpso, that movement is simply too much. I cannot have dry Christmas tree. Okay, but it's also the same for so Fpso, Sevan, but for example SPAR and TLP, they allow for dry Christmas trees. Okay, so the bottom supported and also the TLP and also the SPAR. Okay, actually that was one of the reasons to make the part of the SPAR so long, okay, such that the movement will be limited, and then I can have an arrangement like that. Okay, otherwise I have too much movement, I cannot compensate, and then this pipe will get destroyed. Okay, so I think we're close. I just wanted to have a short discussion on the layout, okay, of the what happens if I decide to go for dry or go for wet. What does it affect? How does it affect the layout of my system? Okay, and how does that affect also my offshore structure? But we keep it for next week. So we have today the delivery, right, of the exercise set 3. I see most of you are in good track. Then we have, I will post, is not the full problem, but I will post exercise 4, the first problem today, hopefully. Okay, so you can look at that soon. And next class we continue with offshore structures. Yeah, the part that was missing, the marine loads and the production system layout.
Will the new habit be 2 weeks from today, or 2 weeks from the final?
No, when the other problem is posted. Okay.
Okay, from the full problem.
Yeah, I just want, if you want to start working on it, that those that want, that they can start. Okay. Okay. See you on next week. Enjoy the weekend.